Okay, as you can see on our table here, or on the smartboard, we're going to talk today about entropy. And entropy is labeled with the capital S. So our learning target is to write and interpret thermochemical equations and use them to calculate changes in Gibbs free energy, which is delta G, of a reaction. So what you're going to see, we're going to do entropy today. Tomorrow you'll have a video over enthalpy, and we'll do enthalpy then on Monday, and the two of those are used to calculate this Gibbs free energy. So we're going to use the entropy, the enthalpy to hit this learning target about Gibbs free energy. Now our success criteria is just simple, sweet and simple, short and simple. Define entropy and calculate entropy. So you're going to need to have your data table out. So grab that data table. Now, what is entropy? Entropy is the measure of the amount of disorder of a system. So the higher the entropy, the more disorder. The lower the entropy, the less disorder or more order. Now, the law of disorder states that things want to move spontaneously in the direction of maximum disorder. So when we think about disorder and order in terms of our phases, which one, solid, liquid, gas, do you think has the most order? Tyler? Solids, yeah. Okay? Because they're packed closely together, they're moving as a part. So there's more order in a solid, the least amount of order or the most disorder is in gases. Also, our entropy increases when we have a substance that is divided into its parts. So, for example, on that particular one, all right, on that particular one, we dealt earlier in the year with potassium chlorate as a solid. We put that in a crucible, we heated it, correct? And we got KCl as a solid and oxygen gas given off. Now looking at this, that's not balanced, so I need to balance this. So let me get this balanced real quick. So now I have this equation balanced. A nice little decomposition equation. We did this in the lab. Now, as I look at this, I can say a couple of things. I have a solid right here. I have a solid with, I have a, dang on it. I have a solid right here. Right there, okay? Which turns into a solid and a gas. So I'm splitting it apart. So I'm getting more disorder by splitting it apart. I'm getting more disorder because I have a solid going to a gas too. All right? So that is what that particular thing means. The entropy increases when we divide it into the parts. Also, the entropy increases when the temperature increases. Well, that makes sense, doesn't it? What phase has the most temperature, the highest? The gas, right? We said the gas has the most entropy. So as we increase temperature, we get those particles moving faster and faster, so we have more entropy. Now, what does this all mean? Well, we are going to use the entropy to do some calculations. So go ahead and write this particular problem down, and it will be the first one that we calculate. Now, I've included the data that we're going to need right here on this lower part. You don't necessarily have to copy that down, but I've included this data. Now, where does this data come from? Well, this is the data table that I gave you from WebAssign, correct? So, one thing that I like about this particular one is that it is in alphabetical order. So when I look right here, I can see where chromium is. Chromium is right down here, and it says 23.6. Now, the thing about this is this chromium right here as a solid says 23.77. I have 3 different tables up here, okay? 3 different tables, and all 3 tables have a different value for chromium as a solid, okay? So, we need to have some kind of a ballpark area. And I think that ballpark on all 3 of the tables, it runs from 23.6 anywhere up to 24. So it's pretty close. The reason I gave you the one that you have is because that one is the one that I got off of WebAssign. Okay, so we're going to use WebAssign's table. Now, when I'm calculating the entropy for this particular equation, what I like to do is I like to get an idea in my mind, first of all, what's going on. So I'm looking here. First thing I look is that here I have 2 reactants that form one product, correct? So what do you think? Am I getting more ordered or more disordered when this equation happens? I'm getting more ordered. So I would think my entropy would be going down, okay? Because remember, entropy is a measurement of disorder. So my entropy, I think, is going down on this particular one. So let's go ahead and calculate that. Well, how do I calculate the entropy? I use this equation. The entropy is equal to the entropy of the products minus the entropy of the reactants. Now, where I see the most errors, okay, where I see the most errors is the fact that the products are on the left or on the right side and the reactants are on the left. Is that the way it goes on the equation? No. But people want to put the products on the left and the reactants on the right. As we should. Well, they want to do it just the opposite. Okay? So make sure that you don't do that. Now, something that is also very important with this is that I need to know my coefficients out in front because I need to multiply my values by them. So, in this particular case, I only have one product, don't I? That's chromium 3 oxide. So, I'm going to find my value for chromium 3 oxide, which is 81.2. And how many of them do I have? 2. So, I'm going to take that 81.2, and I'm going to bring it down here. I'm going to say that I have 2 of the 81.2. Then I'm going to subtract my chromium as a solid, which is 23.77. How many of those do I have? 4 of them. And I am also going to have 3 oxygens that are 205.138. Now, what I do on those is I put a big bracket around those. So I know that I have to do all of these calculations first. So when I take, I'm just going to go through and work these. When I take 81.2, multiply it by 2, I got 162.4. Then I'm going to subtract my reactants. 23.77 times 4 gave me 95.08. My 205.138 times 5, or excuse me, times 3 gave me a 615.414. So I add those two together. So when I added those two together, I got 710.9, excuse me, that's not a 9, 710.494. That should be subtracted from the 162.4, gave me a value of, and let me subtract that, 162.4 minus 710.494 gave me a value of negative 548.094. And when I'm looking at this, I need to sig fig this. So I'm doing addition and subtraction. So I go back up to my original values and I look and I say, okay, this value is in the, what is that, thousandth? This is in the hundredth. This is in the tenth. So I'm going to round it to the tenth. So I'm going to get negative 548.1. And my label, I come all the way back up here. My label is going to be this: joules per Kelvin times mole. So that's my final answer. I predicted my entropy to go down, didn't I? So it actually is. Questions about that? Not real tough math, is it? Now, my second problem here. Go ahead and copy this one down, then I will work it. The problem says, calculate the standard entropy change, delta SO, for the following reaction at 25 degrees Celsius. So basically what this means right here, okay? This delta means the change. This S is the entropy. That tells me the standard, okay? That little O there. So that tells me the change of the standard entropy. Now, when I do this particular thing, where I want to start once again is looking. And I have a solid, I have a gas, I have a solid. So this leads me to believe that as this reaction proceeds, that I am getting more ordered. So once again, my entropy should be going down. I like to start out by finding my entropy of all of my compounds here, so to speak, and elements. So I look at this table, and I need to find, and it's hard to see because it's so small, but up here, the aluminum is right here. ALS, it's the very top one. And I'm using the column right here, the standard entropy column. So it tells me that that value is 28.32. 28.32. So I come back and right here, I just write them. I said 28, didn't I? 28.32. So I write that above my aluminum. Does everybody understand where I got that value from? Okay. Now, my value for oxygen. I come back to my data table and I say, okay, oxygen, where are the O's? I find oxygen, and you see that oxygen is a gas, diatomic oxygen is a gas, and oxygen 3, which is ozone. So make sure you pay attention to which one. I want oxygen diatomic as a gas, and that tells me 205.0. Now my final one is aluminum oxide as a solid. So I look at aluminum oxide as a solid, it gives me 51.00. So now I've gathered all of my data. I just need to work out the problem. Well, I know that my change in entropy is equal to the entropy of the products minus the entropy of the reactants. So I have one product, I have 51.00, and I have two of them. My reactants, I have two, so I'm going to take 4 times the aluminum, 28.32, and I'm going to add to that 3 of the oxygen, which is 205.0. Close up my brackets there. So when I do my math, 51 times 2 is 102.00. I subtract from that 4 times 28.32 is 113.28. And the oxygen is 3 times 205, so that gives me 615. When I add together my 113.28 and my 615, I get 728.28. I subtract that from the 102.00. So when I get my change in entropy, that is going to equal negative 626.3 when I sig fig it. And once again, my label is going to be joules per Kelvin times mole. I predicted that my entropy would go down, and it did, correct? Any questions with this one? Now this last one, I'm going to have you work and then bring it up to me to show me if you got it correct. But before we start, let's look at this. If we're going to guess whether entropy is increasing or decreasing, I look and I say, okay, on my reactant side, I have 2 gases. On my product side, I have 2 gases. So by reading this equation, does it give me any hint whether the entropy is going to be going up or going down? It doesn't, does it? So basically what you're going to have to do is just get the calculations to see what is actually happening. So once you have these calculations done, bring them up to me so I can make sure you are doing this correctly. Once you have the okay from me, you can move on and work on WebAssign 11.3, which is with entropy, or you can work on the video notes for tomorrow.